Well, welcome everyone. Tim Davis here. SuiteSparse GraphBLAS. What's new since HPEC'22? The big thing is the JIT. So now user-defined types and operators are just as fast as built-in types and operators. The CMake system has been modernized. I now have a GXB context object, which has computational resources in it. So for nested parallelism, you can have user threads, each with their own context, defining, hey, this user thread wants to call GraphBLAS with 2 threads, this one with 4, this one with a GPU 1, this one with another GPU in the future. The GRB get and set of the 2.1 C API has been fully implemented. But today I'll focus on the JIT. So the SuiteSparse GraphBLAS JIT. Suppose you call GRB MXM. You've got C, M, and so forth, accumulator, summering, A and B. In SuiteSparse GraphBLAS, I count 2 to the 63 possible variants, possible specializations of this call to GraphBLAS. Each of those 4 matrices has 16 different data structures they could be in. They can be sparse or hypersparse, bitmap and full, by row or by column, isovalued or not, in any combination of those. And they can be any different kinds of built-in types or user-defined types. The accumulator, the summary, could be any one of many built-in combinations, or any of those or partially can be user-defined. The descriptor adds additional options. This is a combinatorial explosion. Many of these aspects of these matrix formats, for example, are not even known at compile time. So even a C++ GraphBLAS API would need a JIT to capture all of these possible variations. So the solution is then a just-in-time compiler. This is what I call the SuiteSparse GraphBLAS JIT. So suppose you're doing an EWISE add, A plus log of B. Now, of course, you could use a GRB apply first and then an add, but suppose you've got some operator you want to use for GRB EWISE add, X plus log of Y. So in the current C API, you say, here's a binary op, here's a function, you compile that function, you pass me the function pointer, and you call EWISE add, and I use that operator, I see a function pointer, and I use that for the EWISE add. Well, there's a problem here. All I have is a function pointer. That's not enough. I need the definition of that function. So you need to call GXB binary op new to give me the name of that function and the string that defines that function in its entirety. That source code. I need the source code of the function as a string. If you have a user-defined data type, so here's an example of a Gaussian integer with a real and imaginary part. Give me quote type def struct int real int imaginary unquote for that. Give me the string for the user-defined function. And also I need my own source code. Where do I find that? If I have all that, then the GraphBLAS JIT can write its own C file, compile it, link it in, and run it. So imagine you're now calling EWISE add from a user application. I have to first enumerate this instance of the call. There's one of, in this case, 2 to the 53 variants for the EWISE add. And I check to see if I have a kernel for it. Do I have a factory kernel already compiled in libgraphblas.so? What I had prior to the JIT? Fine, just call it. Oh, you've strayed outside that domain. Let me look for the JIT kernel. Maybe I've already compiled it and loaded it in. You're just using it again, the same instance. That's very fast. I just have to look at that instance, look this function pointer up in a hash table, call it. Now that function pointer is not the function pointer to the operator. It's a function pointer to the JIT kernel that I compiled for EWISE add for that variation with that operator. Have you compiled this kernel before? Maybe yesterday, and you came in, rebooted, started your application up, started up GraphBLAS again, and it's not loaded, but it's already in your cache folder, compiled. I'll just load it in. What if I don't find it there? Well, then I have to write the C file out to the cache file. I have to call a compiler to create a dynamic library, DL open it, and hash it. And it's fast next time. What if there's no JIT at all? It's disabled. Well, then I have a generic backup with function pointers for the operators and memcopy for the values. So it'll be slow, but it'll work. To do this, I need my own source code. GraphBLAS needs to find itself. Well, where is it? Like if you're a Linux distro maintainer, you distribute libgraphblas.so and graphblas.h. There's GraphBLAS. I need my source. So what I do is I take the required source code I need, not all of GraphBLAS, but just the 24,000 lines of code just for all my kernels. And I convert them to binary, compress them so they're small, and I compile them into libgraphblas.so. GRB init then says, when it starts, it says, well, oh, the JIT's enabled. And there's the cache folder. It's .SuiteSparse GRB 9.0, for example, by default. I look at that and say, is my source code there? If it isn't, GRB init calls a decompression method and decompresses the binary into the source. So there's my source code. Now, this is how the JIT works, but there's other features of the JIT that are also powerful. What if you're in a high-level language like Python or Julia, or an application like FalkerDB, formerly Redis Graph, MATLAB, and so on? What are you going to do? The problem here is that GraphBLAS needs that function pointer sometimes. So I need it, for example, if the performance is not critical, I don't want to compile a JIT kernel. Say reduced to scalar can have an accumulator there. One call to one function pointer. That's not a problem. So there are times when I need that function pointer. That's fine if you're a C application. You have the C call function, you compile it, and then you have the source code. You can give me the string with it, both. That's not a problem. But what in these high-level languages, you could imagine them creating the function string, but maybe not the function pointer, because then they would need a C compiler as well. No problem. You let me do that. Give me the string alone. Give me a null function pointer. This does not return an error. This tells me, Tim, just compile it yourself. I take the string, I create a JIT kernel for just the function pointer. You can also do this with user-defined data types. Suppose you create a type-def struct, int real, int imaginary, for a Gaussian integer as a user-defined type. Now that's 8 bytes, right? Well, are you sure? How do you know, unless you ask the C compiler what the size of that type is? No problem. If you don't know what the size of that type is, you just tell me when you create the type, you say, here's a type, it's size 0, and here's the name of the type, and here's the string that defines it. That 0 tells me that you don't know the type? Fine, I'll find out. I'll compile a JIT kernel, and all it does is inject that string, stick size of around it, and there you have it. I have a JIT kernel that all its job is to find the size of that user-defined type. And there's another feature of the JIT, which is very powerful. I call it the pre-JIT. So suppose you're an application, a high level like FalkerDB, and you want to create JIT kernels for all the things you do in your database, the graph database, for FalkerDB or Julia maybe, or Python GraphBLAS interface. But you don't want to give access to the compiler to JIT kernel creation for the end user. So what you do is you use the pre-JIT feature. During development time, you turn the JIT on and you walk your application through all its paces. Say FalkerDB, you do a bunch of graph queries. You let me compile lots of JIT kernels. You can even turn off my factor kernel, so GraphBLAS becomes very short, very small, very easy to compile, very fast to compile, and everything goes through the JIT now. And then you stop. You shut your application down, and now you go look at your cache folder, and it's full of C source codes that I have created, and also the library versions. You don't need the library compiled libraries. You take all those C files that you find there, or some of them, whatever you like, copy them back into the GraphBLAS main source in a folder called pre-JIT. Rebuild GraphBLAS, and that's it. The CMake magic will find them and embed them now as pre-compiled kernels, pre-JIT kernels, into libgraphblas.so. It's been augmented by those JIT kernels for your application, all pre-compiled. And so now in this process of looking for kernels, I will find them. They'll be pre-hashed. GRB init then pre-hashes them. And so what happens here in this process of, it won't be a factory kernel, that's they're JIT kernels, but they'll be as if already loaded JIT kernels is how the pre-JIT is treated right here in this third bullet. So that's the GraphBLAS pre-JIT. It allows you to have a very compact GraphBLAS library. So those are the main features of the new features since HPEC'22. And thank you for your attention.